Hi everyone, welcome to today's talk. First we have Carl Mummert talking about coding in reverse mathematics.
All right, thank you. Yes, good morning, everybody. Figure out what button works to change the slides. All right, so I wanted to thank the organizers for this great workshop and for inviting me to speak. It has been very much a hybrid. It's very interesting for me. And so this talk also is a first for me because it's less purely mathematical than I'm used to. But I wanted to talk about a couple things that I think may be of interest to both philosophers and to people in reverse mathematics. Dabir and I had mentioned the book that is just about to come out. We don't have a great and lengthy discussion in there. We have some remarks in the introduction, but maybe this also expands a little bit on the thoughts we had when we were writing that. So I wanted to start with, from my perspective, a few comments on sort of the trajectory of the field of reverse math, especially since 1999. So in the first, say, 2 to 3 decades, there was a lot of work in reverse math and second order arithmetic. There was a very, very productive period in the 1980s. And then by 1999, Steve Simpson's text, absolutely a classic, covered all of this. But of course, since 1999, there's been quite a few things that have also happened. So a few things that I think are important, and without going into everything and obviously missing some important things. So by 2001, which was about the time that I came into the field, so on the one hand, there was much more interest from computability theorists, I think, more broadly. So what I mean by that are people who'd worked in computability before and not in reverse math, began to be more interested in, at first, using reverse math just to produce alternative statements of their theorems, right? So they could get a corollary in reverse math sometimes for every other result they proved. But also there was this work of, it's a little polemic, but it's not completely false, right? It's nice if you can get 2 for 1. So, but
I think that's still true.
yeah. There was also this this very intriguing work from Siedepin that took a while to be understood. Also this paper of Cherlach-Jokic and Slayman on Ramsey's theorem that showed that there was a lot more. Previously, Ramsey's theorem was somewhat viewed as mysterious, right? It was this sort of exceptional thing. Now, of course, there's been enormous amounts of work in the last couple decades on Ramsey's theorem. And then the other large development, there were 2 papers, one by Girardi and Marconi, one by Dore, Zafarov, Hurst, Maletti, and Schaefer, that both discussed this reduction, which is Weirach reducibility, which Weirach had proposed quite a bit earlier, but which was unknown in the reverse mathematics community, although I'm sure it was known in the Weirach style community. And that realization led to, well, first, a very nice communication between 2 research groups that previously had not interacted very much, and also to this idea of using reductions as well as reversals as ways to compare the strengths of principles, to separate principles. Reversals are nice for showing things are equivalent, but if things aren't equivalent, then how can you separate them? So all of this showed that there was a lot of growth still to be had. And so, by now, 2022, I think it's fair to say in reverse mathematics, there are at least 2 things that people do, right? They use formal theories of arithmetic to determine, the minimal axioms that you need to prove principles. And we also use a number of things from computability theory, degree characterizations, definability characterizations, but especially reducibilities to characterize the strength of solving the problems that are associated with those theorems. And so, in our mind, back and forth, you have a principle, you have a problem. They're not viewed as especially different. They're different aspects, maybe, of the same theorem. So that is where, in my mind, where things stand today. So to do all of that, you have to code or represent things, right? So the question is, how do you represent a mathematical problem or principle, if those are different, along with the objects that it references, if you want to study the computability strength or the logical strength, right, of the principle. And of course, that's especially important for computability theory or second order arithmetic, because your fundamental objects are just natural numbers or sets or functions. And so you need some way to represent other objects if you want to talk about them. So this has been, and it's been from the beginning, right, one of the key questions, right? So which coding methods are the best, right, is another question compared with what are the weakest axioms that you need to prove a theorem. And just as an analogy, or maybe to set up my point of view, I want to point out, in quantum mechanics, right, we have a quote from Dirac, right, but this is a well-known phenomenon. So we can observe an object only by letting it interact with some outside influence, and an active observation is necessarily accompanied by some disturbance of the object observed. Right, so Dirac is talking about this in the context of quantum mechanics, but I think the exact same thing is true in terms of formalization of mathematical theorems. Right, the representations and the formal systems that we use to analyze the strength of a problem have, I would say, a necessary and unavoidable impact on the strength that we measure. Right, the way that we formalize something is always going to affect the strength, and that's regardless of what method we take. Now we can try to minimize the effect, we can try to control the effect, right? But there's going to be an effect. This is just one thing that we see throughout reverse mathematics, right? That we make choices as we formalize things. And so that leads you to ask, well, what choices do you make? What are the aspects of those choices that you consider, right? That's what I want to talk about today. I also wanted to briefly mention, right, also maybe to set up the way I want to look at things, a few motivations for reverse mathematics. So we've heard at the workshop several times about foundationalism, right, the idea that you're trying to choose either a preferred system and then recreate mathematics within that system, or to create sort of a single definition for a mathematical object so that you can then view that as the definition. So that has been a motivation of constructive mathematics and reverse mathematics for a while, but there's several others, right? So Friedman has mentioned for a long time the goal of showing that seemingly weak statements inherently imply strong axioms, right? That's a very nice thing if you can do it, right? To show that some principle which seems very innocuous already implies some very strong logical principles, right? And to make that sort of argument compelling, of course, you need the principles to be represented in a natural way, right? If the representation itself seems very strange or seems very complicated, then it undercuts the argument that the strength is somehow inherent in the theorem. So computability theorists, and maybe you'll find this more fair, Peter, may be motivated by either exploring the computability theoretic aspects of mathematics, right? So what computability is inherent in Feynman's theorem? What computability is inherent in Ramsey's theorem? Or to find new methods and applications for computability theory, right? You have a nice set of tools, you have a nice way of thinking, and you'd like to find some place that you can work. So Shor describes omega models as the playground of logic, I think, right? Like it's a nice place to go, use some tools and have a good time. Then the other thing that we could look at, right, thinking more as mathematicians maybe, is that if there's a concept of the internal combinatorics, right, the way that a theorem really works, well, maybe we can use computability methods to help understand that, right? To help understand why it is that some combinatorial theorems we can prove from others. And that's something you see even in purely combinatorial literature, right? It's very common to prove one combinatorial theorem by reducing it to another just in informal mathematics. So is there some internal combinatorics we could study? So we see this, in the huge literature on variations of Ramsey's theorem, or combinatorial consequences of model theoretic properties, or combinatorial consequences of analytic theorems of analysis. So these are other motivations, right, that could lead you to want to represent things and to want to study what we call reverse mathematics. All right. So I was saying, if we're not thinking foundationally, right, we're not necessarily trying to give a definitional representation of something. We're not necessarily trying to say the real numbers are quickly converging Cauchy sequences, right? We're saying for our purposes, right, in this analysis, we're going to represent them in this way. And in fact, we often see that studying the same theorem using several different coding methods reveals more about the theorem than just studying it from one perspective. Right? I would say, right, just to reinforce my opinion that you cannot avoid this sort of thing, right? Even the choice of the logic that you use, right, affects the strength of the theorem as you're going to see it, right? It affects, in some way, the precise theorem that you've stated, right? The same formula, right, written as a formula of L2 has a different meaning if you interpret it in constructive reverse mathematics compared to interpreting it in classical reverse mathematics, right? So it's just, in my opinion, unavoidable. You'll have to make some of these representational choices, like I said, not only in the statements you use, but in the way you interpret them logically. All right. So one example many people have seen, but I'll come back to it, so I wanted to state it formally, is the coding system that we use most often for continuous functions. So a continuous function code, if you were to look at, say, Steve Simpson's book, is a set of 5 tuples, but it's really an enumeration of 4 tuples. And you have these 4 tuples, x, r, y, s, and really what it says is that a certain closed ball in the domain maps into a certain closed ball in the range. That is the intended interpretation of this code. And of course, you need to know more than just one ball. You need to know a lot of these facts, maybe not all of them, but enough of them to recover the image of any particular point, right? So continuous function code is an enumeration of a lot of these facts about a continuous function, and enough of them and consistent enough for you to evaluate the function. So this type of coding, well, we use it everywhere, in second order arithmetic at least. And from the beginning, there were many questions, right? Is this a reasonable coding system? Is there a better coding system for continuous functions? This was a question, as far back at least as the 70s, if not before. And we'll see when I move on to higher order reverse math, a way to make that question a little more precise, right? To actually have a mathematical theorem about coding systems. But this code will come up several times. All right. Another thing that we see sometimes before we get into coding in detail is something that I call miniaturization. I think this is the way it's used in the literature also. The idea is that you have a very general theorem, and we're going to narrow it to only talk about some special class of objects. In our case, that's typically going to mean countable or separable objects, right? So instead of saying every linear order has an increasing or decreasing sequence, right? Instead, we can say every countable linear order does. And from general mathematical facts, we know that's not really much of a weakening, because if you have any linear order, you can take a countable subset, it will have an increasing or decreasing sequence from the miniaturization. That's an increasing or decreasing sequence of the original order, right? So modulo every linear order has a countable subset, right? It's not that different. You could say every countable commutative ring, right, has a prime ideal, right, rather than every commutative ring, right? You could restrict a theorem of analysis to just separable spaces, right, rather than stating it for arbitrary spaces. So on the one hand, we need to do that to formalize things in second order arithmetic, right? We're not going to be able to talk about linear orders of arbitrary cardinality in Z2. It also helps, right, from another point of view, avoid unnecessary generality, which is related to what I think Bishop called pseudo-generality, right? But if we're thinking that we want to be computable mathematicians, we want to think about the computability theoretic interpretations of what we're doing, right, then generalizing to uncountable linear orders, right, takes us out of the realm of computability somehow, right? So if we want to try to make things a little more specific, these miniaturizations help to do that. Of course, they are miniaturizations, right? They're not the full theorem. In some cases, they're close. In some cases, well, they're further away.
So do you know an example where the miniaturization doesn't imply the full thing? I mean, you want to think, like your example here, you're just after increasing or decreasing sequence, right? So I'm wondering about the step.
I think that there are, but I'm going to have trouble coming up with one on the spot here. I think the issue is that it has to be when the conclusion of the theorem actually refers to the full size of the original object in some way. So
how would it work for something like the prime ideal theorem for groups or something? What would that even mean? You take a countable subgroup, or how would it imply?
Well, that's one thing. I mean,
so the pigeonhole principle for arbitrary sets, right? If you finitely color an arbitrary set, then one of the colors has the same cardinality as the original set, right? The miniaturization would only give you a countable, right, homogeneous set, but you want one of the same cardinality you started with. So,
but I guess I feel that these are all just projections of some higher cardinality things down to
right.
arithmetic,
yeah.
And that theorem is fine. And if you wanted to actually look at the higher cardinality thing, you could just use a bigger system and everything would work.
No, this is true, exactly. The reason you miniaturize it all the way down to countable is especially so that you can put it in second order arithmetic. And this is where, when I mention higher order arithmetic, this is one reason that you don't have to miniaturize as much in that setting, because you can code larger objects. You don't have to make everything countable.
But I believe if you could get the thing work down in second order arithmetic, it should work fine up above.
Not exactly.
I don't think that's always true, but I think we can find examples.
I know
Yeah.
you're talking about countable here equals given by a sequence. To most mathematicians, countable means an injection to it.
So we can talk about that also, because there's a quirk of miniaturization, which is that most people ordinarily work in set theory, where, for example, you can flip functions either way and there's no strength to it. So whether you say there's an injection from the set to n or from n to the set are in normal mathematics completely equivalent. But as you come down here, you start to see differences, and this affects things. But in any event, we look at miniaturizations as one way, right, to represent a larger theorem in the context of a smaller system. A particular example I want to mention that we'll come back to a couple of times is related to topology. So Francois Doré has a notion of a countable second countable space. So that's a lot of countables, but it means the set of points is countable and there's a countable basis, right? So this, of course, is not a class of topological spaces that topologists are particularly interested in. All the topologists who I know are actually mostly interested in very uncountable spaces. But it is a class of spaces, right? It's a miniaturization, right? By looking at spaces where the set of points is countable, we can directly represent the space in second order arithmetic and see what happens. So the set of points would be a subset of n. We would have a basis, which is just a set of or sequence of subsets of n. And in this definition, there's an extra uniformity. There's a function that helps witness the definition of a basis, right? So the definition of a basis says if a point is in two basic open sets, then there is another basic open set around the point contained in their intersection. And so we sort of scholemize that with this function k to add some uniformity. So roughly speaking, a strong CSC space is represented in that way. And a weak CSC space is similar, except that the basic open sets are enumerated rather than being given as decidable, right? So here, when I say that you have a set of sets, I mean the question is K in BI is a uniform question relative to K in I, right? In a weak space, it would be a uniformly sigma 1 question. So again, does this capture all of topology? Well, of course not, right? But it miniaturizes it and puts it into a framework where you can see some aspects in second order arithmetic. All right, so I'd like to talk about 2 or 3 characterizations, issues, aspects of codings that I think are either unspoken by reverse mathematicians or not spoken about directly enough. But there are things that, for people who do reverse math, I think you'll think are obvious, right? This is, of course, what you think about. And the first of them is something that, I don't know, for lack of a word, we'll call fullness, right? And what I mean by that is the extent to which a representation of some class of objects captures the entire collection that we're trying to refer to. And in practice, you'll see that this is uniformly the case in reverse mathematics codings, that they have this fullness property, although nobody tends to mention it. They might state it as a theorem, they might not even state it as a theorem. So what do I mean in examples, right? Every countable field has a code, right? In the standard model of second order arithmetic, every countable field has a code. Every complete separable metric space in the standard model, the full model of second order arithmetic, has a code. Every continuous function does have one of those convoluted continuous function codes. Every topology on the natural numbers, that's second countable, I should say that, has a representation as a CSC space, right? So this is a fundamental consideration in reverse math, that we're trying to code full classes of objects, right? And that differs from some other programs. I mean, most notably, maybe like Markov-style recursive mathematics, where a real number is an index to compute it, and therefore any real number that's not computable like simply does not exist, right? Like that coding is certainly not full, right? But in reverse mathematics, we don't look at that sort of coding.
You're always meaning as a coding the full.
In this model. Here, I mean in the standard model, exactly. Because once you have that sense, you can effectivize it to get a notion of computable object. And of course, not every object will have a computable code because of cardinality, yeah. But in the standard model, right, this is if I came up with a coding for metric spaces and not every metric space had a code of that sort, someone would point this out in reverse mathematics. They would not do that as a normal aspect of the field. But of course, exactly as you're saying, right, once we have the full model, we then specialize it down to rec or down to some other model. in order to see what happens in like when we're outside of the standard model. So questions about this fullness also arise if you consider multiple representations. So back to our continuous functions, right? In third order arithmetic, you could represent a continuous function, say from R to R. You could represent it directly as a third order functional, right? That in this case, if it's supposed to be R to R, needs to be invariant on equality of codes of real numbers. Or you could represent it as a continuous function code, right? And so you can formalize the question of fullness by asking, in third order arithmetic, is it the case that every representation of one sort has a representation of another sort, right? That's also a question about fullness, right? Just formalized, in this case, into third order arithmetic. We'll come back to that and see how difficult it is in just a minute. The other thing that fullness does actually is it leads you to interesting questions. So it's not hard at all to represent, if you have a complete separable metric space, to represent, which is countable, so a complete countable separable metric space, as a weak CSC space. I'm sorry for the typos, right? And the reason you can do it as a weak CSC space is because you only have to enumerate the basic open sets. And in a metric space, open balls generally are enumerable in a certain way, right? It should be a sigma 1 property whether a point is in an open set. But what if we want to work with strong CSC spaces, right? So this question, I think the answer is yes, but I don't have a proof of it at the moment. But I would very much think the answer should be yes, right? Is there a computable, countable, complete separable metric space? Maybe you could phrase that in fewer words. I'm not trying to economize. But is there a space of that sort that's not effectively homeomorphic to any strong CSC space? Right? And effectively homeomorphic means that there are uniform ways of pushing the open sets forward and backwards. Right? So this question, right, isn't a mathematical question. It's a computability theory question, right? But it comes up from the question, is that coding full, right, with respect to this class of spaces? And the thing that makes this question a little more challenging, it's not just asking for the open balls to be non-computable, right? It's asking for there to be no computable homeomorphism whatsoever, right? Even if that changes the basic open sets. It's not too hard, I think, to make a computable, countable metric space in which every rational open ball around a particular point is uncountable, right? That is a construction that's not so bad. But if you ask, like, not only are the open balls non-computable, but no basis whatsoever works, right? That's where the challenge in this question comes from, right? But it's a computability question, right? Inspired by this fullness consideration. The second consideration of the three I'm going to mention, I think, is something that I would call directness. I'm not saying for the philosophers that these are very well defined, but I think they're questions, right? And there's a lot that you could ask about them. But somehow, right, what you want is for the coding to be close to the way that you normally would think about the objects. So something that's very direct, right, the way that we code countable algebraic structures, right? So if you have a countable group, you just code it as a subset of the naturals, a function from G to G, which is the group operation, right? That is about as direct as you can get. The continuous function codes are much less direct, right? They, in some way, once you see that they're about closed balls, at least you can see where the definition arose. But it's not the way that any normal textbook would discuss continuous functions, right? It's something that we use because of its utility. Another aspect, though, of directness is that it's one of the things that allows us to work in non-standard models, right? So a quote from Sam Sanders, right? He pointed out that the codes for objects are not only meant to represent the original objects in the standard model, but they're meant to continue as well as possible to represent the original objects even in non-standard models. Even if the natural numbers are not standard, we still want the coding to give us something that acts like what we expect. So for example, complete separable metric spaces in second order arithmetic in a non-standard model pretty much act like normal complete separable metric spaces, right? Countable groups coded in a non-standard model act like countable groups, right? You don't notice that you're in a non-standard model, and you shouldn't, right? I mean, it would be very strange if the behavior of something depended on whether you're in a standard model or not, right? But we try as well as possible, right, to make sure that that happens, that the coding is not sensitive, particularly to being in a non-standard model or a standard model.
Do you have an example where this does not happen? Maybe just built up on purpose.
The easiest way for it to fail is if you need a lot of induction for the coding to work, right? So that would be one way, and that's one reason why our coding systems tend to not rely on a lot of induction. But I don't have, at the moment, I don't have a great example.
In third order arithmetic, there are some, like, you could add to O max RC0 little omega. You could add the second order statement, all reals are recursive. You can add that to RCA0 too. In RCA0 little omega, if you say all reals are recursive, then, going back to BC, all functions on the reals are continuous. But in RCA0 proper, you can still have codes for discontinuous functions. So there's this connection between second and third order objects, namely recursive reals imply continuous functions. And that's why you shouldn't cut off at third order or any order for that matter, because of these connections.
But the thing that lets us prove that the objects continue to act the way they should, right, is that the axioms about the coding, right, are phrased in usually like universal, relatively concrete ways, so that we can, so that the properties we want continue to hold in non-standard models. Like this, I think, is a key aspect. And the third aspect, right, that kind of goes against directness is utility, right, which is a sense of what can we do with the representation, right? A representation is great, but if you can't do anything with it, if you can't prove any results, right, then you're not going to do any reverse math. So we heard yesterday from Ted Slayman about Cauchy sequences that were unmodulated, so to speak, right? Cauchy sequences that simply follow the definition of Cauchy. But in reverse mathematics, as many people know, right, we only work with quickly converging Cauchy sequences, right? And that means that you have essentially a way to Skolemize the convergence, right? So that if you'd like to approximate the limit to within some epsilon, you know how far out in the sequence you need to go in order to approximate it, right? That's different than the Cauchy sequences, as we saw yesterday, which could, head to one place for a little while, change their mind, head somewhere else for a little while, change their mind, go somewhere else. You have no way to tell if the sequence is serious about where it says it'd like to go, right? So out of utility, right, to be able to use a sequence to approximate the limit, right, we'd like to have that information. That leads us to use quickly converging Cauchy sequences. Continuous function codes, among other things, allow you to compose functions, right? Another coding method that you might like for a continuous function in second order arithmetic would just be to have the value at every rational number, right? And then somehow use that to evaluate it by taking limits of rationals and using continuity. And that may or may not work, but what you won't be able to do very easily in that way is compose functions, right? Because you don't have the values at non-rational numbers to compose with. Continuous function codes, although they're a little bit obscure, in RCA0, you can produce a composition, right, of two continuous function codes, right? You can add 5 to a continuous real valued function and produce the continuous function code for that function, right? You can do all of the ring theoretic operations on continuous functions, right, directly from those codes, right? So that utility is one reason why that coding is used, right? Because it allows you to perform these operations. The other nice thing about continuous function codes and the overall setting for the real numbers is that they become a special case of complete separable metric spaces. So that every theorem about complete separable metric spaces immediately applies to R, because R is represented directly as a special case, right? Otherwise, you'd have to prove a theorem twice, possibly. You'd have to prove it for metric spaces in one representation, and then turn around and reprove it for R in another representation, right? Or maybe you'd have one representation for R and another for R to the omega, or something like this, right? So using the same representation for the broad class makes it easier, to take special cases of principles. The other way that that utility shows up is as uniformity, right? And so in some cases, that means adding additional information to the representation. What I mean by uniformity, right? Well, it's what we always mean in computability. Maybe it's a little hard to say, but it means that, you can produce the result that you're looking for in the same way for a large set of inputs, right? Based only on the actual inputs, but the method itself doesn't change. So in CSC spaces, that function K that helped you enumerate the intersection of two basic open sets, right? It's there specifically to give you uniformity. You could assert as an axiom, right, the definition of a basis. For every two basic open sets at every point in their intersection, there is some basic open set around them, right? And if you only needed to do that once, right, in a proof, in classical logic, you could just grab the one you need and work with it. But if you need to do it over and over, right, if you need to do it as part of some, construction by recursion, right, you might need it to be uniform. The representation of reals with quickly converging Cauchy sequences, one benefit of it is that it makes addition and multiplication uniformly computable, which is not true for Dedekind cuts, right? This is a significant challenge for Dedekind cuts. They define the reals perfectly well, but in terms of their computability properties, they don't respect the ring operations very well. But with Cauchy sequences or the signed binary expansion, which is essentially the same thing, you have these uniform methods for doing operations, which means you can write one formula that you can write down in second order arithmetic for addition, right? This extra information, by the way, is sometimes called constructive enrichment, right? This is another term that I've seen used, I believe, for the same idea, right? Which is that we have a definition, right? But on its face, it doesn't provide us enough resources to work with something. So you enrich it, you add a little more information, right? In Bishop-style mathematics, that might mean adding a modulus of uniform continuity to every continuous function on a compact set, right? It's a constructive enrichment that allows you, in terms of utility, to do more. And then, the last factor, right, in all of these, right, is some sort of judgment, which I realize, right, is a cop-out in some ways. It's not a precise thing. But there was a nice quote from Dennis Hirschfeld that I wanted to mention in that regard, right? Sort of a justification that he mentioned near the beginning of Slicing the Truth. We should never disregard the fact that formalization usually entails losses as well as gains, right? Simplifications and compromises must be made, and aspects of the original problem are left out of the picture. There are likely instances in which the answers in the formal setting are unsatisfying, but enough answers of genuine interest can be given to justify the method, right? So this is the trade-off, right? You'd like things that are very direct, right? Things that maybe stray very little from the normal definitions, right? And that would be great, right? But in other cases, you have to move a little further away, but hopefully you can justify that through the results that you get, right? As in any other area of mathematics, right? The theorem in some way speaks for itself to justify the hypotheses. So just to summarize this section, right, fullness, directness, utility are certainly not the only considerations for evaluating a coding system, right? But I think they are important, and I'm sorry for the typo, I think they are important considerations. And I think that they're implicit as you look at the reverse mathematics literature, especially if you don't work in the area, right? These questions are in the heads of the people writing the papers, even if they don't translate onto the page, right? These are the sorts of questions that you're taught early on to think about whenever you're writing something. The next part of the talk is going to be a little on coding and its relationship with higher order reverse mathematics, but keep these in mind as we go there, right? Both that, any way you go will have strengths as well as costs, and that, right, in some way, the results you get help to justify the costs. All right. So higher order systems, reverse mathematics, as we've heard, as everybody knows, traditionally has been carried out in second order arithmetic. I was saying, right, more recently, I think the field has expanded to include much more in the way of computable reducibility than it used to. So it's not as much only second order arithmetic, but traditionally, certainly second order arithmetic is very closely tied to reverse mathematics. But there are several reasons, I think, to look at reverse math in higher order arithmetic as well. So on the one hand, there are principles that you can state in higher order arithmetic that you just can't state in second order arithmetic. Some objects have much more direct representations, right? You have now in third order arithmetic functions from the reals to the reals directly, right? So you don't have to look at these continuous function codes. And higher order systems, they let you look at some aspects of computable reducibility, right, that you wouldn't be able to look at as directly in second order arithmetic. They're also tied much more closely with proof theory and with constructive mathematics in many ways, right? So those fields for a long time have used higher order arithmetic rather than second order arithmetic. So it's very natural, right, to think about reverse mathematics in higher order arithmetic. Now, and this is a criticism that I know is actually relatively valid. We don't actually use higher order arithmetic, right? Maybe we use fourth order arithmetic. I bet we never go beyond eighth order arithmetic, right? But we never use 50th order arithmetic. Like, I know of no principle of type 50 that we've ever looked at, right? So in some way, the very high types are just a superstructure that float around, right, above the low types that we actually care about. But of course, as happens, it's more convenient to define all the types at once than to try to define things by special cases. If you try to draw a line in the sand, of course, you'll find some situation where you need something one higher, right? So it's more convenient to just work in arithmetic in all finite types. But in practice, we're really talking third, fourth, fifth order arithmetic. The other significant difference is that higher order arithmetic is function-based rather than set-based, right? In classical logic, that's not too much of a distinction, right? Because you can turn a set into a characteristic function or a function with values 0 and 1 into a set. But it does have some other aspects, because evaluating a function in higher order arithmetic is an atomic operation, which is boggling to the mind for a computability theorist, because I learned computability when I was very young. Evaluating a function is an iterative process, right? First you compute the first bit, then you compute the second bit, then you compute the third bit, right? That's how you evaluate a function. But in higher order arithmetic, you evaluate a function by putting in the input and reading the output, right? There's no use principle, there's no step-by-step computation. You can't put in half of an input and get out half of an output, right? So there is a difference in a function-based system, because when you have a type 2 function, you have to put in an entire real, and out of that you will get an entire real.
It's the Lambda calculus.
Exactly. Yeah. So everything will be coded as a function. The main operation is function composition, and sets, will be represented by characteristic functions. So Kohlenbach, right, based on systems that were very well known, right, but maybe not interpreted in reverse math, had proposed some higher order systems that are useful. One challenge in higher order reverse math is finding comprehension axioms that are useful. At the level of type 2, there are several, like this E2 we'll talk about. At type 4 or 5, again, I don't know of very many type 5 comprehension axioms, right? Like, it's not as obvious what they would be. I could tell you some. I mean, there's some obvious ones, but there's not very many, certainly not of a range of strengths, the way that in second order arithmetic, you have a very nice, right, variation of strengths of set existence principles. But so Kohlenbach proposed for the higher order version, RC naught omega, a system, we don't need the formal definitions, that's EPRA omega and a principal quantifier free axiom of choice. The key point about that system is that it's L2 conservative over RC naught. I mean, that's why he justified the name RC naught omega, right? That, if you can prove something in this system, its translation into L2, right, will be provable in RC naught. So in particular, it's compatible with every function on the natural numbers being computable. For AC naught, one way to get an analogous system is to use this principle E2. So E2 essentially says that there is a functional of type 2, which tells you if an arbitrary function from the naturals to the naturals ever takes on the value 0. Right? So this thing, E2, it says yes or no, is there an n with f of n equal to 0, right? The 0 versus 1 is not a significant difference in classical reverse math, right? Or even in constructive reverse math, where the natural numbers tend to have decidable equality, right? It's just easier to use 0 than 1, because 0 is maybe directly a term of your language. And so this system, RC naught plus E2, is L1 conservative over PA, right? So, and that's the same way that AC naught, right, is L1 conservative over PA. So this is another justification for the name. Like, why is this like AC naught? Well, at least for arithmetical statements, it's conservative over piano arithmetic. Yes?
Sorry, just one question. Do you have a recursive function that does those reductions for you? Or where are those conservative results proved?
So,
Are they model theoretic results, or are they proof theoretic results? Like, do you have...
Oh, they're all interpretations, yeah.
Okay.
Yeah.
Okay.
And these interpretations should both be in Kohlenbach's proof theory book.
So to go from RCA 0 little omega to RCA 0 proper. So you use what is called the ECF interpretation.
Yeah.
Yeah, and so what this does, it's mind-boggling, I know. It takes any third order object or higher and replaces it by reverse math code. So if you, this is, I mean, if you, what more do you want, you know, like, you have all these crazy third order things flying around. ECF just replaces them by what Carl just showed, reverse math codes, and it's a statement in your language.
Yeah.
Then of course you know that this E2, for example, the discontinuous function, that's interpreted as a 0 equals 1, of course, because there cannot be a continuous code for a discontinuous function. But yeah, so these are many aspects. The problem is Troelstra wrote this down somewhere, this ECF translation. It's not very readable.
But is sorry, just a quick follow-up. Is the translation itself the ECF translation and primitive recursive function?
Yeah, essentially.
Yeah.
I mean, like probably something like linear time.
Yeah, I know, it's syntactic, so yeah.
Yeah, very syntactic.
Yeah. So I want to mention, we'll come back to them again, 2 omniscience principles, right? So it was very fortunate for me, first that I get to speak last, but also that other people went ahead and talked about things that I was going to mention. So we've already heard about Cauchy sequences, we've heard some about omniscience principles, which, right, as choice principles, right, are throughout constructive reverse mathematics, but begin to become important in higher order reverse math, right? In second order, not so much. So LPO says, if you have a function, either it's always 0 or it's not always 0, right? Now, in classical math, it doesn't matter whether I state the quantifiers positively or negatively. In constructive math, you'd have to be very careful about the statements. Whether you want to state it as a for all or an exist will make a difference. But I can be a little sloppy because I'm only in classical logic here. So LPO says if you have a function, essentially, you have a way to tell, does it have a 0 or is it always 0 or is it not always 0? Of course, if you know it's not always 0, in principle, you could search, right? But how will you know if your search will never end, right? That's what LPO does. And then LLPO, slightly weaker, essentially says if a function is non-zero at most once, then either it's always 0 on the odd numbers or it's always 0 on the even numbers, right? So again, classically, this is trivial, right? But in constructive analysis, we know LPO is stronger than LLPO, and they both appear often enough that they're pretty important principles. Right, if you're wondering about the fact that they seem trivial classically, right, imagine thinking of this in like the BHK interpretation, right? You wouldn't be able to realize this with a computable functional, which is why it's relevant in higher order reverse math. Okay, so let's talk about discontinuous functions first. This is sort of a key dichotomy in higher order reverse math. So Kohlenbach showed in this setting, although I think the method dates back to previous work from Grilio, that E2, that principle that we saw for AC and OT, is equivalent to there being a functional that's not everywhere sequentially continuous. Right? Or if you wanted to look at this more uniformly, Kratka and Girardi showed that if you have any function from n to the n to n that's discontinuous anywhere, then LPO Weyrach reduces to it relative to some oracle. Right? So that oracle has to figure out like where is the discontinuity, how do you witness that discontinuity, right? All of that is in the oracle, right? But the point is that relative to some oracle, any discontinuous function, right, Weyrach computes LPO, right? So getting something discontinuous you expect to be non-computable, right? But this gives you a measure of the non-computability in some way, right? It's E2 in the context of four-ball systems, or it's at least as strong as LPO relative to some oracle. All right. I was saying some third-order principles simply can't be stated in second-order arithmetic, like there's a discontinuous function, right? To state that we have a function on R, we have to give a code. We can only give a code for a continuous function because the coding method is so intertwined with continuity. So to say there's a discontinuous function, right, you require a higher order statement. You could say every open cover of the real line has a countable subcover, right? So in second order arithmetic, that would become trivial because every open cover would be interpreted as every whatever enumerated open cover. But here we mean genuinely an uncountable open cover, right? Every open cover of 0, 1 has a finite subcover, or there's no injection from the unit interval to n. All of these, right, can be written very naturally in third order logic and can't in any way that I know in second order. All right, so Eastaugh and Sanders have talked about something that they've called coding overhead, which is the strength that it takes, right, if you have a representation in third order arithmetic to convert it to second order arithmetic, right, to sort of bridge that gap. And so what I want to do next is to look at that for continuous function codes and for open sets. So for continuous function codes, there's an older paper from Cole and Bach, right? So there's first this characterization and then some reverse math. So these are equivalent over RC and automega. You have a function that's represented by a continuous function code in the sense that I put earlier, or that the function has an associate, right, in the sense of Kleene-Kreisel, or that it has what's called a continuous modulus of pointwise continuity, which is really, if you think about it, what our continuous function codes do, right? At a given point, a continuous function code gives you a way to produce arbitrarily good approximations to the output of that point, but that also means it lets you figure out how close do I have to be to this point for the output to be sufficiently close to the output.
You don't need continuity of the modulus.
That's very possible. I hope that I copied this literally from his paper.
This is definitely
Yeah.
cool, but you don't need
Okay,
continuity.
just that it has any modulus of pointwise continuity, yeah. So the reverse math for this turns out to be WKL, which is actually a little surprising, but it's very nice. So Kohlenbach showed in WKL, you can produce continuous function codes for functions on the Cantor space, but it doesn't reverse to WKL. RC and automega plus even a little more choice doesn't prove that every continuous function on Cantor space has a code. And some stronger system, EPA omega is stronger than PRA omega. I mean, that must be true, right? Because PA is stronger than PRA. But this stronger system, along with every continuous function has a code, is second order arithmetically conservative over the stronger system with slightly weaker choice. Right. So you can't necessarily form codes effectively in third order arithmetic, although the existence of the codes is somewhat conservative once you get to high enough systems, but you can form them in WKL. Right? So this type of result, right, it does several things, right? First, it gives an analysis formally of coding overhead. And this is something in reverse math that we often talk about, that you don't just want to say one system seems stronger than another, you want a formal result that shows it. Like in what formal sense, right? So this formally shows you something about coding overhead, right? It shows you in this system you can form the code, in this system you can't, right? Now the situation is a little complex, that's how things are, but that's what you get if you want it to be formal, right? So I think this is sort of a very nice use of higher order reverse math, right? To analyze these coding problems in a way that's genuinely formal, rather than just, well, we don't know how to code another way or something like that. The second example I want to look at is with open covers. So I was saying in third order arithmetic, when we want to represent an open set, the most direct way to do it is just with a characteristic function. This point is in the set, this point is not in the set. And to say the set is open is just a sentence that says, right, given every point in the set, there's an open ball around the point that's completely contained in the set, right? So in second order arithmetic, on the other hand, we represent an open set by enumerating a sequence of, rational balls, essentially. Actually, we enumerate a sequence of codes of rational balls, right? Because that's what we could do. So again, there's a question of coding overhead, right? If you have an open set, right, in the third order sense, how hard is it to represent it in the second order sense? So this is a theorem of Norman and Sanders. So they define a principle open that says every open set in third order arithmetic is actually covered by a sequence of open rational balls, right? So this principle is exactly solve this coding problem. And what they show is that, again, in the higher order setting, that should say pi 1 k Ca naught omega. This lowercase 1 here should be a k. That's why there's a k there. But it is provable in this strengthening of Z2 omega that Sam talked about in his talk, right, where you add this principal E3. So this is harder than the continuous function case. In the continuous function case, you could do it in WKL, right? And certainly by the time that you're at the level of ACA naught, whatever that means, in third order arithmetic, that problem with coding continuous functions will go away. But in this case, it's not going to go away at anything like that, right? This issue of going from an open set coded as a characteristic function to an open set coded as an enumeration of open balls, right, is very hard to solve. Like, it's a fundamental gap, right? And it leads to different reverse math, right? Depending on which way you represent your open set, you're going to get different strength, right? Because apparently, right, if you have an open set in this third order sense, you won't be able to enumerate open balls that cover it, right? You'll have to do something else. All right. Now, one phenomenon that we also see, which I don't have an explanation for philosophically, is that if you have a hard problem and you make a variation of it, that variation will also be hard for different reasons, right? So things that are difficult in classical second order reverse math are also difficult in constructive reverse math, but for different reasons. And they're also difficult in set theory, right? Although the statement in set theory is a completely different statement, right? But it will also be difficult for some other reason. Right, so for open covers, we can see the same sort of phenomenon, although the underlying proofs are completely different, with CSC spaces, right? So a subset of a CSC space, now we can use the normal definition in second order arithmetic because we can quantify over points, right? So the set is a set of natural numbers. It's open if, for every point in the set, there's a basic open set around the point inside your open set. We can write that, right? This is the benefit of miniaturizing things, right? Now, remember, the basic open sets and this open set U are going to be they're going to be infinite, right? We're not going to be able to directly effectively tell which basic open sets are inside U and which ones are not, right? But the points being countable, we can at least deal with. So a theorem sort of implicit in Doré, these are equivalent over RCA naught, regular reverse math, either saying that you have ACA naught, or saying that every open set in a strong CSC space is the union of a sequence of basic open sets. So this is the similar phenomenon, right, that Norman and Sanders have, right, but miniaturized, right? You can still see this issue, right? So there's something about this, right, that's not completely effective, even though it's a different setting. Okay. All right. Moving on to another thing you could do in higher order reverse math, which I think shows one of the downsides or one of the strange behaviors of it. So viewed as Weirach problems, say, LLPO is strictly Weirach less than LPO. This is true. I was saying, right, constructively, right, they're one is weaker than the other. In the Weirach sense, which is completely different, you still have this fact. So you might think, if you're in higher order reverse math, that you should just put in a realizer for one of these principles or the other. I mean, now you can do that, right? You have functionals, you can put in realizers. So you could imagine a realizer RLPO, right, that scholomizes the quantifier in LPO. Or you could imagine a realizer RLLPO, which again scholomizes the quantifiers in LLPO, right? And in this sense, by the way, the realizer for LPO in the literature is also called Pfefferman's mu, right? Just to complicate things. So you can imagine, okay, let's do that, right? I have this. So things that you would expect, right? It certainly is true. I already said LLPO is strictly Weirach below LPO. LLPO hat, the parallelization, is Weirach equivalent to the Weirach problem WKL. And Kohlenbach showed that the principle LPO has a realizer, which is just to say Pfefferman's mu, is equivalent to E2, right? None of this is new. None of it is too surprising because we expect LPO is kind of like a Turing jump. E2 is kind of like a Turing jump. These should match. LLPO hat is about WKL, right? That's another sense in which LLPO is weaker. Okay, so here's the more surprising part for me. I was surprised when I learned it. So over RC naught omega, LLPO has a realizer, is the same as E2. Right? Even though in every other sense that you would normally care about it, LLPO should be weaker, right? But also the principle that WKL has a realizer, right? Is it not equivalent to WKL? It's equivalent to something at the level of ACA naught.
Yeah, but you should add to that, like, for example, the fan function, or like that computes modulus of uniform continuity for a continuous function, that's below E2. So here it's just LLPO is fundamentally unconstructive and discontinuous in a sense.
Yeah, we'll get there.
The
Yeah.
contraposition is much better behaved.
This is true, and this is a good point, that another distinction that you see in these higher order settings is that, a realizer for a principle is not the same as a realizer for the contrapositive of the principle, because the quantifiers are very different, right? So again, how you write it, how you phrase the quantifiers will affect what you get as a realizer, which in turn will affect the strength.
And this is a defect of Weyrauch that you sort of have to pull out of Vasco almost. The realizer for the fan theorem is just computable, which also, I mean,
Yeah.
WKL is equivalent to
Yeah.
fan. Why? That's the defect of their framework.
So, no, and every framework has its challenges, right? But the reason this happens is that in higher order arithmetic, every functional is total. I mean, this is just the fundamental nature of the system. So in principle, right, in a perfect world, LOPO is a problem defined only on certain instances, right? It's not a total problem. But the realizer is a total realizer. And in particular, the realizer is a discontinuous total realizer. So you fall back to this theorem that we mentioned from Kohlenbach. Anytime you have a discontinuous functional, you're going to get E2, right? In the perfect world, right, you'd have a way to have realizers that are only defined on certain values, right? And it's not that the particular value that LLPO takes off of its natural domain is important. It's just the fact that it's defined there at all is the problem, right? It wouldn't matter what value it had, right? Just the fact that you've sort of totalized something that shouldn't be total, right, causes these sort of blow-ups in my mind.
But in Weyrauch
Yeah.
analysis, where there are partial functions,
Yeah.
then there are the total continuation of
Exactly.
partial functions, which very often are much stronger than the original function.
Exactly. That's exactly what we're seeing here, exactly, is that, and even in classical computability, right, we know there are partial computable functions on the naturals that have no extension to a total computable functional on the naturals, right? Extending is not a safe operation. So in the Weyrauch degrees, this is true. Here, right, it causes this effect because everything is total in higher order reverse math.
This is
Yeah.
why Dyck Nolman wanted to introduce this Lambda calculus version of his 1 to his 9,
Yeah.
because there you do have partial stuff flying.
Yeah, I think that this is a real project for higher order reverse math, is to find a system that is more comfortable with partial functionals so that you don't have this phenomenon. But let me talk through the strengths and the weaknesses, and then I'll wrap up very quickly, I promise. So things I think are beneficial, nice about higher order reverse math, right? I view it as an alternative in this way, right? It doesn't linearly directly extend second order reverse math. It really just goes in a different direction. So on the one hand, you can directly state these principles. You can formally study coding overhead, right? Which is really an advance, right? I remember reading papers that were written in the early 80s about continuous function codes, when they were wondering, is there any way that we could find a formal method to study the strength of these coding systems, right? And the answer is yes, of course there is. The ties with constructive arithmetic, I think, are also very nice in higher order reverse mathematics. The downsides, well, they may be upsides depending on your taste, right? But the downsides, on the one hand, higher order reverse math is tied with higher computability theory, right? Rather than classical Turing computability theory. Right, so this is already, by reputation, a much more intricate subject, right? Certainly less well known, right? And it causes many more complications. There are many fewer methods for constructing models, right? We have very powerful methods for constructing models of second order arithmetic. There are relatively fewer methods for constructing models of higher order arithmetic with very fine control over the reals, right? You can construct models, but controlling them in the way you do for combinatorial principles, we don't have yet. And I was saying that the totality of all the functionals adds information, right, which really might not be what you want, right? So in some cases, you have to avoid stating principles in terms of realizers, even though you've now moved to a setting where that would be the natural way to state them. All right, so just to wrap up, I think, my viewpoint on reverse mathematics, right, beyond the strength of theorems, is that we're really looking at how hard it is to solve problems. We can measure that by proving theorems, right? By getting reversals. We can measure it with Weyrauch reducibility. We can measure it in various ways. And getting a complete view, can require both work in formal arithmetic or sometimes multiple formal arithmetics, as well as work in computability theory. The coding and representation, right, are unavoidable in this setting because you're looking at the same theorem in many settings. You're going to have to represent it somewhat differently. But there are aspects you can consider. There are ways you can control it, and you can actually study it formally as well. So that is my talk. Thank you.
All right, does anybody have any questions?
But for this issue with the coding of continuous function, that clearly works for functions on the counter space, right?
I believe it extends to stronger things. So this one,
Yes.
yeah. So if
You were mentioning, yes, restriction to the counter space.
yeah,
right?
so it extends at least to the closed interval, and I think to even the reals with more work. Is that right, Sam?
I don't think WKL can do it for
Not for the reals, but for 0, 1.
0, 1, for example.
Yeah.
With some,
Okay, because that, okay.
So-
Common space.
Yeah, there's yes.
But
Yeah.
general case, say Bayer space.
AC is 0.
Okay.
I mean, E2. So it's not
Yeah.
that crazy compared to the stuff Dak and I have looked at.
Yeah.
Okay.
Yeah.
So
No.
it starts to get a little bit iffy if, for example, you say, what about a function, third order object, that is, say, continuous on a given Rm closed set. So you have not any crazy set, a reverse math closed set, and you define a third order function, and it has to be continuous on that set, and you want to extend it like
Yeah.
pizza and all that. Then you already get very different answers. So, but there again, what Carl said was actually very insightful. It was very nice talk.
Oh, thanks.
So it has to do a lot with the totality of the third order object have to be total. I mean, I usually just I would say, well, ask Ulrich, he did this, and then Ulrich would say, yeah, it was per Martin Löw who, because Martin Löw type theory is everything is total too.
I think Harvey has a question.
Okay. Do I need to do?
Okay, my official question is, what do you think of my comments? I can talk about them instead of you.
Yeah.
Have you read it? I think you were busy giving a talk while I wrote it, right?
Oh, that might happen.
Why don't you? I try that.
Yeah, we can't see the chat either, so.
Let's try.
If you could ask it as a question, that might be easier for me.
Oh, okay. I'm making a suggestion. Let's see if I can. Okay, so I guess what I'm kind of suggesting is what I would call, I just thought of this, I would call reverse coding theory.
Yeah. Mm-hmm.
In reverse, if you look to this, I didn't get a chance to even begin to talk about that in my talk, but I'm beefing up the notes on the talk now. So soon, for the meeting, I will leave it with something. The easiest case is very simple. Let's say you have the semi-ring on the naturals. All right, the ordered semi-ring. Well, there's a thing called the ordered semi-group on the integers, right? Now, normally, instinctively, a normal coding theorist would say, well, we can code integers by integers by naturals, comma, a bit, right? Positive or negative.
Yeah.
And proceed to define the ring operations. And nobody would bat an eye, right? I mean, clearly, intuitively, this is the obvious way to have integers and not just naturals.
It is?
And there's a gut feeling that it doesn't make any difference and there are no issues, right? So one can make this into a theorem, right? Now, what I'm suggesting is I make this baby case into a theorem where you actually introduce another sort.
This is interesting because in my mind, there's the representation in algebra. You should represent the elements, if you go from a semigroup to a group, as differences, so as pairs of natural numbers. But is there a way to make it precise that is smoother than this number?
Okay, I would regard that as an alternative that actually probably is not. Many people would like that maybe even better. You're right. Historically, you're right, and I wouldn't know. That would be an interesting question. What's better about it? But my point is that when you do this, either way, there's a sense in which you can prove that both those codings are completely correct, because what you can do is you can put down a theory, which actually gets quite long, by the way, a little bit annoyingly long, which has two sorts, naturals and integers, and all this crosstalk between them, which you have to make sure you've got it all down right, and with the obvious axioms. That theory is really what you want to look at, and you want to say that each of these individual codings are synonymies or interpretations with strong properties.
All right.
Okay, so now that's actually a little harder than you think to actually pull that off, because you have to really make sure you've written down enough about the interactions between the naturals and the integers. This is just the first baby example. Another example would be, the next one to do would be integers and rationals. So you have the ordered ring of integers and the ordered ring of rationals. And you want to write down the axioms. You want to write down the axioms that you want. In other words, the interaction axioms. And then you want to show that these codings are correct. The codings everybody uses. Again, there's probably a couple of different variations depending upon how nice you want to be about it. Now, when you get to higher order matters like reals, and especially when you get into abstract matters that also are higher order, like Polish spaces, then the issues are much more delicate, and you're going to start with. So with the reals, you'd start with you'd have sets of natural numbers from the beginning. Then you get sets of integers, right, as before. But then you get sets of rationals. I mean, I'm talking about redoing the previous stuff with sets. And then you have the reals. You have the Dedekind. You have the stuff for the Dedekind ones. Then there's the ones for the Cauchy ones where you have to use sequences from the beginning, as well as, you should use. Okay, but I just want to give you an idea of the kind of program I'm talking about, where step by step. Yeah, so you'd expect, for example, with the Dedekind thing and with the Cauchy thing, you get different principles, which are incompatible and so forth. And then obviously sequences, infinite sequences is where the shit really hits the fan. And you explore this axiomatically with reverse coding. Now,
I think there's
what has to be done is this has to be built up all the way through reverse math and all the way through higher order reverse math. Otherwise, I think you don't have anything of foundational, of any serious foundational significance without doing this.
There's a nice paper from Jeff Hurst. I think it's called Representations of Reals in Reverse Math, where he essentially does these comparisons. There's been some other work also, but that paper really does, in a way, contribute to this reverse coding, I think.
Okay, that's good. I guess he's probably asleep, right?
Jeff, I don't know. I don't know if he's here or not, but.
Okay, I take a look at that. I didn't know about that. But I'm saying that I don't regard any of this, especially higher order, higher than 2 particularly, any of this is legitimate reverse mathematics in the sense that I meant in 1967 to 76.
I agree.
I do not, and I know how to, and I'm claiming that this is the way to fix it, but it's quite a lot of work and quite a lot of serious issues to do this. For example, I had to work quite hard to show that there was any logical strength in logic, in math logic at all. You know, I mentioned that last in my talk. If you remember this, I called it the straw man. I don't know if you were at my talk, but this,
I was.
I set up this straw man and it knocked it down.
But we know,
And it was actually quite difficult to do so.
I mean, we know that the completeness theorem in set theory, right, is like the Boolean prime ideal theorem. So it's another example where you expect to see that difficulty come up, and it does in second order arithmetic as well, right? Like, so there's logic, there's definitely strength in mathematical logic there.
We need to talk about this offline. I mean,
All right.
I'm not the only person who has a question for your talk, I'm sure.
Okay, great. Are there more questions online? I can't see anything here.
Yeah,
I don't trust to touch it.
yeah, I don't.
Yeah, sorry if you can hear me. I just wanted to point out that if people are interested in talking to Harvey further than that, check your emails. There's an email sent on his behalf about joining him for. John, if anyone happened not to be able to get it or something like that, I'm putting the meeting ID for the Zoom meeting here. It'll happen right after the end of this, and people can talk to him. Anyway, just wanted to point that
Great. If there are no more questions, let's thank Carl again.
Thanks.